Hi, welcome to the next lecture on Haskell. In this lecture, we will look at a new concept, which is how you can define your own data types. Okay, so far you've become used to using data types that Haskell provides for you. Of course, given the data types that Haskell gives you, you can build some of your own, like you can form your own pair type int char, let us say, or list of int or list of int, etc. Haskell provides you some basic features of combining existing types into new ones, and it gives you a stock of built-in types. But there are new types that the user can define on her own. We will look at how to do this in this lecture. Okay. The most important thing is that we use the data keyword to define new types. There are two keywords that you need to remember. Type is one, data is one. Type introduces a new name for an existing type. New name for existing type. Or what is called a type synonym. Whereas data introduces a new data type. We'll see that many of the built-in Haskell data types themselves are built using the data keyword, and you will see it in the, if you go to the Haskell page and try to see the Haskell standard libraries, you will see the code itself provided to you, and you will see that even very basic data types have all been defined using the data keyword. Okay. For instance, bool. Okay, bool is defined using the data keyword, and it says data bool equals false true. There are only, so these types are called enumerated data types. You can list all values. You list or enumerate all data values in the type. There are only two values in bool, false and true, and you are listed them. And as I mentioned earlier in a previous lecture, based on the order in which you list the values, that induces an order on the data type. So false is less than true actually. Okay, that is because that is how it has been defined in Haskell. We will see how to actually make this happen. You can define your own data type. Well, let's define a data type for day: Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. These are the 7 names of the days. You list all the names and you put this vertical line here, right? You should read it as a day is either Sunday or Monday or Tuesday or Wednesday. So this vertical bar stands for or. Okay, so if you want to read, you read it as a day is either Sunday or Monday or Tuesday or ... Okay. Similarly, an int is either I don't know what the min value is, either min bound or min bound plus 1 or and so on, but this is not how it is defined. Okay, so integer has some built-in representation. So integer is too primitive for it to be defined in this manner, because this manner you will see that it's not the simplest, the most efficient manner in which you store things. So integer has some internal representation, but conceptually you can think of int as min bound or min bound plus 1 or min bound plus 2 or all the way till 0 or 1 or 2 all the way till max bound minus 1. Okay. Okay, so you can conceptually think of it like this, but internally integer is so basic that Haskell uses the internal machine representation to represent integers and not an enumerated type like this. Okay, fine. Okay, so that's about enumerating the values in a data type. You can also have types where there are multiple kinds of values, but each value will have its own parameter. For instance, shape is a type that you want to define. Data shape. A shape is either a circle with double. The double here stands for radius, or square and a double argument. This stands for length of the side. Or a rectangle, but rectangle needs two parameters, length and breadth. Okay, so I can now define a list of shapes, list of shape. So this is circle 3.0 or square 4.0 or rectangle 3.0 4.0. Okay, so you can have things like this. Now, just like you defined functions using pattern matching on the basic types, you can also define functions on your user defined types using pattern matching. Here is a function weekend, it's of type day arrow bool. Weekend Saturday is true, weekend Sunday is true, weekend anything else is false. Area, shape arrow double. Okay, area circle r is pi times r times r, pi is built in, part of preload. It's of type double. Area of square is side times side. Area of a rectangle with length L and breadth B is L times B. Okay, so you can define things like this. Right, and now once you have an area function, you can actually do things like map area on circle 3 square 2 rectangle 4 3. You can do pretty much anything that you used to do with functions. You can create a list of shapes and then you can map a function on this list of shapes. Yeah, and this should give you the appropriate value. How about the following function? The same weekend function, we earlier defined it using pattern matching. Weekend Saturday is false, is true, weekend Sunday is true, weekend anything else is false. Now we could try to ask weekend 2 of D, D stands for a day, D equals Sat or D equals Sun. This is what we want to use. If we try this on GHCI, you will get an error. No instance for EQ day. That is because GHCI does not know it, Haskell does not yet know the day belongs to EQ. Remember, EQ is a type class, a collection of types. Day is a type. So whether day belongs to EQ or not, Haskell does not know it. In fact, as far as Haskell is concerned, day does not belong to EQ because it is a new type that we have defined and we have not mentioned anything about the equality checks being allowed on values of type day. So to fix this, okay, one more example before we fix this. Next day, we want to do this. Next day of sun is Monday, next day of Monday is Tuesday, and so on and so forth. Next day of Saturday is Sunday. So far so good, it's fine. This program will compile. But if you load this program in GHCI and try to run it, right, suppose let's say next day of Friday in GHCI, what you will get will be an error. It will say no instance for show day arising from a use of print, because remember, you say next day Friday in GHCI, GHCI wants to print this value. Printing the value means first converting it to string and then putting it on the screen or whatever output device you are using, right? And it doesn't know how to convert it into string. Okay, so okay, so this is the problem. So typically any so what you need to do is, you need to, whenever you create your own data type, you need to add it as an instance of some existing type classes. So typically you want to, whatever new type you create, you want to make it an instance of an instance of EQ as well as show. Okay, so so to check equality of two values of a data type A, there must be an EQA instance. So you use the deriving keyword. This is a new keyword, right? So far you have learnt two new keywords, data, deriving. Okay, deriving says that you derive a make day an instance of EQ by providing a default implementation of, by deriving an implementation of equal to. Okay, that is what this means. Okay, how does Haskell derive an implementation of equal to? It applies some standard rules. It will say, oh, Sunday is equal to Sunday, Monday is equal to Monday, Tuesday is equal to Tuesday, etc. Sunday is not equal to Monday, Monday is not equal to Tuesday, because you listed these values separately. So separately listed values are distinct and every value is equal to itself. That's all. Okay, so Sunday is not equal to Monday, Monday is not equal to Sunday, Monday is not equal to Tuesday, and so on. Okay, so distinctly listed values are not equal. Okay, that's all there is. Okay, so now so you get the default behavior like Sunday is equal to Sunday, Tuesday is not equal to Friday, etc. Now if you run this, we will show this example in a demo session. Weekday 2 will compile without an error. Okay, and to make the next day function work in GHCA, you have to make it part of the show type class as well. And typically when you create any new data type of your own, you will make it part of EQ and show by saying deriving and within parenthesis EQ comma show. Okay, you can list a lot of type classes here. So I am making day part of both EQ and show. Okay, but now if I want to compare between 2 days, so yeah, but how does show also a default implementation of the small show, small s show, the function. So a default implementation of show of type day arrow string is derived. That's what you mean by saying deriving show. What is the default implementation? Show ved is ved within strings, within quotes, okay, and so on. Okay, that's it. You can also create an ORed day instance. You can say ORed, and then this will automatically list Sunday to be less than Monday, to be less than Tuesday, etc. Because that is the order in which you listed these values. Okay, and now this explains why in bool false is less than true. Yeah, so you have this behavior. You can also create other things. You can create an enum. Enum is another type class. This is the type class of enumerable values. What all do you need to make something enumerable? You need a notion of next element, okay, and you also need a first element and a last element. It should be finite. The number of values in the data type should be finite, and there should be a notion of a next element. Okay, so that is when you can enumerate. Okay, so here so when you have the enumerate, maybe you don't need the first element and last element, but you at least need the notion of a next element. And when you have enumerate, you can use the list notation 1 dot dot, okay, 1 dot dot 10. Okay, similarly I can say sun dot dot Thursday. That will list all values from Sunday to Thursday. Okay, so you can now, and the moment you have enumerate, you have something belongs to the class enum, you have a notion of successor. Successor of Tuesday is Wednesday, predecessor of Friday is Thursday, and then you can say list all values from Sunday to Thursday. Okay, so these are all things you can do as part of the enum class. ensures the availability of these functions. Okay, good. So now we have seen some the data type and how you can make it part of many many type classes. And you can similarly do instances for shape as well. You can say shape is circle double, square double, rectangle double double, and then you say deriving EQ, ORD and show. These are the 3 type classes that you are deriving for shape. And now the and you have default behavior. Show circle of 5.0 will just put circle 5.0 inside double quotes. Square 4.0 will just equal to square 4.0 will result in true. Square 4.0 slash equal to square 3.0 will also result in true. Circle 5.0 slash equal to rectangle 3.0 4.0 will also result in true. The point is that the square is the same. This is a square, that is also a square, but the sides, the values differ. This is a circle, but that is a rectangle. So no matter what the parameters are, circle is not equal to a rectangle, so you will say they are not equal to. And because you defined it to be ORD, this list of square 2.0, circle 3.0 and square 22.0 is less than the list square 2.0 and square 0.005, because square 2.0 is the same as square 2.0. But when you come to the next element, circle here and square here, circle 3.0, which is fine, but circle is listed first. This is the first listed value, kind of value. And square is listed second. So circle is less than square according to this definition. Okay, and it doesn't matter that the square side is very less and the circle radius is huge. That doesn't matter. All you care about is that whether it's a circle or a square, circle is less than square according to this definition. Maybe you can have saner definitions of less than. Yeah, so notice that deriving only make a type, make a data type part of a type class by providing default behavior. This is the important thing, default implementation. Okay, this is the important thing. Okay, if you want custom implementations, you need to use a new keyword called instance. Okay, you want to do custom implementations of some function and make a data type part of a type class, then you use the keyword instance. Yeah, and you do it differently. For instance, for shape, we could say instance ORD shape. Shape is an instance of ORD where less than or equal to is a function that I am going to define now of type shape arrow bool. How do I define this? Shape 1 less than shape 2 is defined to be the same as area of shape 1 less than or equal to area of shape 2. Okay, so this less than or equal to, this is the comparison operator on shape. Type is shape arrow bool. Whereas this, if you take this part of the definition here, this less than or equal to is comparison operator on double. Because I am comparing the area of shape 1 with area of shape 2. If area of shape 1 is less than or equal to area of shape 2, I am deeming shape 1 to be less than or equal to shape 2. This is an arbitrary definition that I am making just for illustrative purposes, right? But this is how you define it. So this is comparison operator on double, and this is of type double arrow bool. And this feature where you use the same symbol to denote different operators is called operator overloading. Different from polymorphism, because polymorphism in Haskell means that the same code works over different types, whereas operator overloading means that I am just using the same operator to denote two different operations where the underlying computation is different. Okay, so the less than or equal to on shape is something where I compute the area of both and then do a less than or equal to comparison on the double values. Less than or equal to on double is some built-in thing. I will use some hardware level operators to compare between two double precision numbers. Okay, okay. So the less than or equal to on the left is being defined, the right hand, the left hand, the less than or equal to on the right is being used and is of type double arrow bool. Okay, so now I could also for instance create, it is not necessary at all that you should say deriving, not necessary that deriving always. Deriving means that you are using a default implementation, but I could use my own. I could, for instance, define my own show method. Show, to define shape to be an instance of type of the class show with a capital S. So this line is saying shape is an instance of class show. Or in other words, there is a show instance of shape. Okay, so you use this terminology. You can use any of these terminologies, but the point is shape belongs to the class show. Let us think of it that way. And for that you need to define a function with a small s show. Okay, and this function should be of type shape arrow string. And I could say, for instance, show circle r is a string which says circle with radius, and then I show r. This show is of type double arrow string. All this. Show square of s, I could say square with side, and then I could add plus plus show s. Or show rectangle LB means rectangle with length show L and breadth show B. Okay, I could do things like this. This is more informative. You could do this. Yeah, so this is the point. Okay, and I could also have my own equality. Okay, I can say instance EQ shape where shape 1 equals shape 2 is the same as saying area of shape 1 as usual. This is being defined and is of type shape arrow bool. Whereas this is being used the type is double arrow bool. Okay, so yeah, so just to summarize, you can use deriving, default behavior, or instance, and get custom behavior. Okay, let's move on now. What are these things? So shape was either a circle or a square or a whatever. Day was either Sunday or Monday or whatever. These all have a name. They are called constructors. Okay. Constructors are just functions, but they start with an uppercase letter. Note that usually in Haskell, types start with an uppercase letter and functions begin with a lowercase letter, but constructors are functions that start with an uppercase letter. Sometimes they are functions like this. Sunday is of type day. Is it a function? Yes, it's a kind of a degenerate function. It's a function that takes no argument at all. It's in mathematics, you might call it a zero array function or a null array function, or in other words a constant, right? Because it doesn't even expect any argument, it provides a value, namely Sunday. So Sunday is of type day, rectangle is of type double arrow shape, circle is of type double arrow shape, okay? And since these are just functions, I can use them just like I would use any other function. I can apply circle on 5.0 and I will get shape. I can do map circle. I can have a list of double and I can do map circle and I will get a list of shapes, okay? Like here. Okay. So, right, so this is about it. I can partially apply this thing. So, I can apply square to, not square, I can apply rectangle 4.0 and this will be of type double arrow shape. Right? I can also apply constructors partially, just like I can apply functions partially. I'll have a function of 2 arguments, but remember function of 2 arguments are really functions of 1 argument which return a function of 1 argument. So rectangle is a function which you provide 1 double and then you will get a something of type double arrow shape. Okay, you can do this also. Okay, fine. Okay, and then let's just look at some syntactic variations here. Sometimes you might have a data type with a single constructor. So far we have seen that you will have data types where values can be of different kinds. So shape is either a circle or a square or a rectangle. Day is either Sunday or Monday or Tuesday, etc. Okay, an arithmetic expression is either a simple number or adding 2 other expressions or subtracting 1 expression from another or multiplying 2 expressions or dividing 1 expression from another. Okay, so there is choice here, but sometimes there is no choice, in which case you will you can call them records, okay, because it's like a record in a database where there is a bunch of values that you put together as part of one unit, but it's to be treated as one unit, but there is no choice, okay, you yeah. So there is a Haskell convention which is that, so far we had shape was the data type, this is the name of the data type, let me use a different color. So when you have shape is the name of the data type, circle and double square are the names of the constructors, and double the type of the parameter to the constructor. Okay, so this is what we have so far. But in case you only have a single constructor, then the Haskell convention is that the data type name is the same as the constructor name. Okay, so here I am storing details about a person, string int, double string. This string, the first string is the name, second int is the age, double is the height, and the last string is the email address. Okay, so name, age, height, email. Okay, that's what it represents, and I have this thing. I could have records, some girl whose data is here, her name is Ashwini, age is 21, height is 5.9, and the email address is ashwini@me.com. Okay, so that's a record, right? It looks just like a database record, so that's why it's called a record. So the 4 parameters are supposed to stand for name, age, height, and email ID. How do you extract the height of a girl? You have to write a function for it. Okay, so you'll have to say you need, so these are called constructors. The opposite of a constructor is what is called a destructor. Here you have a single constructor, but you will have each parameter of the constructor you can pull out, right, by, and that's called a destructor. So here are the 4 destructors: name of type person to string, name of, notice that just like you in pattern matching, when you gave pattern matching for lists, you said f of x colon x is inside brace, inside parenthesis, right? Similarly, you will have to put parenthesis around this constructor. This value, the value is the person, the value constructor applied on 4 parameters. You don't care about the second, third, or fourth parameter. The first parameter is in. If the first parameter is in, then the value that you want to return is in. Okay. Similarly, for age, age applied on a value which looks like person applied on the person is the constructor, value constructor. By the way, constructor, value constructor, data constructor all mean the same. Okay. We will later see another kind of constructor called type constructor, but whenever we mention a type constructor, we will explicitly say type constructor. When we just say constructor, we mean value constructor, and these are functions that produce a value of a type. Okay, these are value constructors. Okay, and the value is person applied on something A, something, something. In that case, the age of that person is A. Okay, this is the thing. And height of person, the person constructor applied on something, something H and something is H. Email of the person constructor applied on something, something, something and E is E. Okay, these are the, so name, age, height, email. These are all called destructors. They take the value of a particular user defined type, typically in this case when it is a record type, and it returns the various parameters in the value. The various parameters used in constructing the value, right? This is clearly what you want. You want to select a particular field of a, in database terminology, these destructors are nothing but what you will call select. Select name from this record is what you want to do, or select age, etc. Right? So there is an alternative syntax when you have such a situation, and you can use what is called record syntax. Okay, and what you do is you can name the fields as you build the, as you define the type. You can say data person. Once again, this is the type, and this is the value constructor. And then within braces, you provide the name of each field. Okay, these are all fields. And then the type. So you say name of type string, age of type int, height of type double, email of type string. Okay, and then you say deriving show. Okay, once you have done this, you don't need to, no need to explicitly write destructors. Under record syntax. Because these names also serve as the corresponding destructors, as you will see. Yeah, we can name fields while creating the value of type person. So you will say gal equal person with name equal to Ashwini, height equals 5.9, email equals ashwini@me.com, age equals 21. Note that order of fields can differ. Because you are naming each field, named fields. You can also do it in the original thing, unnamed fields. These are unnamed fields. But if you follow this practice, then you will have to maintain the order. Okay. If you use named fields, you can switch the order around, but if you use unnamed fields, then you have to maintain the order. Okay, fine. The field names are actually functions. So name is of type person arrow string, age is of type person arrow int, height is of type person arrow double, and email is of type person arrow string. So these are actually destructors. Some more examples. So we have now seen a few things. We have seen some basic data types being defined. We saw the deriving keyword, we saw the instance keyword, okay, and then we have seen record syntax. Okay, you can do various things. For instance, here is a way of defining complex numbers as a data type. Data complex equals complex double double. Okay, this is the name of the type. Once again, this is the name of the value constructor. Okay, and you can say deriving equality. And now I can define functions. Absolute value of a complex number is of type complex arrow double. Absolute value of complex xy is nothing but square root of x squared plus y squared. Okay, right? Because and you can define your own custom OR and show instances. You can say complex number 1 is less than or equal to complex number 2, because there is no less than or equal to mathematically defined for complex numbers. I can just give my own cooked up definition. I will say that one number is less than another if their absolute values are, if the absolute value of complex number 1 is less than or equal to the absolute value of complex number 2. Okay. I can do show, where I remember that you will usually write a plus ib. I can write so show of complex of (5.0, 3.0) will actually show as the string 5.0 plus I times 3.0, right. So you will have such things. Okay. Okay. Note that the show here and the show here are of type okay. How do you extract the real and imaginary parts of a complex number? You write destructors. Real of complex x, anything is x. Imaginary of complex anything y is y. But since this is a record really, because you are just storing two doubles and there is no choice of how you vary this thing. So you can use record syntax and you can say data complex equals complex, where which consists of two fields, real of type double and im of type double. Okay. Now you can actually use this to define your earlier functions. Absolute value of complex x is square root of real value of complex number is square root of real part of complex whole squared plus imaginary part of complex whole squared. Okay. So you can do things like this. Okay. And yeah, here we have actually used the destructors. Okay, good. So let's move on. You can also define your own polymorphic types. For instance, here is a classic. This is a just a representation of the built-in list type. Actually, even so fundamental a thing as lists in Haskell is actually very similar to user-defined data type. Okay, so it's exactly this, isomorphic to this, if you will. data list A is nil, is either nil, which corresponds to the empty list, or it is the construction of a list by adding one element of type A to a list of type list A. Okay. List is not a, this is the important point, list is not a type, but it is a type constructor, okay, because there is a parameter here, there is a type parameter here. So list is a type constructor, nil and constant, nil and cons, or sometimes you will just say constructor, or if you want to emphasize, you will say value constructor or data constructor. And you can say deriving EQ ORed, okay, so whichever. For any type A, list A is a type, and nil and cons are the value constructors or data constructors. Nil is of type list A for any type A whatsoever, cons is of type A arrow list A arrow list A, okay. So that's what has been given there. Note that you can't use record syntax, because record syntax is useful only, can be used only when there is only one constructor, okay. So now two values of list type list A can be compared for equality or order, provided the type A itself is an instance of EQ or ORed, okay, and this is automatically enforced when you use deriving. And you can create your own custom functions, and this thing you can say instance show A, as long as A is showable, list A should also be showable, okay. Here is a just like in functions you wrote ORed A implies, for type of a function you wrote ORed A implies list A arrow list A. Here you will say list A is an instance of show, provided A itself is an instance of show. And here is the smallest show implementation that you have. So you will say show L is, you put a left bracket plus plus go L plus plus right bracket, and then go nil is nothing, the empty string. Go cons x nil, if it's the singleton list, you just show x, so you will get x in between this. Or if it's multiple this thing, you show x, you put a comma and then you put a space and then you print the rest of the list, okay. So if I have show cons 1, cons 2, cons 3 nil, I should get the string 1 comma space 2 comma space 3, okay. So I will get something like this. And now if you can define your own list, then you can actually do some better behavior, right. I can say head, so function of type list A arrow maybe A, head of nil is nothing, head of cons x anything is just x, and I can have my own tail like this. Tail is of type list A arrow maybe list A, tail of nil is nothing, tail of cons of anything x's is just x's, okay. If you can define your own data types, you can define your own custom nice behavior like this, okay. So we will stop with this, we will continue with more user defined types, especially recursive user defined types in a future lecture. We will also have a demo session where we will show some of these behavior, okay. Hope you learned some interesting material in this lecture. Thank you.